Good afternoon, everyone. Nice to see you. Standard old thing. I hope you've had a good week so far. It's getting really close to the end of term. A couple of people have asked in the live chat. They've said during the standby screen, can you see, what was it? Is it just me or can we see through the beach overlay in the bottom right of the screen? You can on the standby screen. That's actually the top right corner of my video up here. Um, which I do because I learned the hard way that when I'm showing you a screen, um, what happens is that I can't it disconnects my phone camera. So basically, I leave it there. It also helps me figure out whether it's connected. So if I take you back to the standby screen, you'll actually be able to see, like, if I point my finger up here, you'll be able to see my finger in the bottom right of the screen, somewhere down here. It's like, yeah, so anyway, that's what that is. So that's just me connecting my camera so I can test that it works before we get started. Because last term I had a lot of lectures that started and the video wasn't working, and then I was fumbling trying to get it all together. So that's my. There you go. There's a fun fact, boring fact for your Thursday. So, um, what we're gonna. So today is hopefully a shorter lecture. Every time I say that, we have a tendency to run perfectly on time. But um, this whole week of sorting used to be like a full week of lectures, like a full 4 hours. But two things happened, I think. One is that I already spent a while talking about bubble sort and sorting previously. And then secondly, I took out another sort that we used to teach called shell sort. Just because, again, I think this course covers, like, this course doesn't even cover everything. So it's like you got to draw the line somewhere. Because of that, we might finish this week a bit earlier, which is totally okay, because I'm sure you're all not just like, oh my god, I need more content in my brain. And today we're going to talk about Quicksort for a lot of the first hour, and then we'll just kind of chat about the third part of assignment 2 for the for the next part. Um, and we're actually are going to talk more about. Oh, that's right. And then there's another type of sort called a heap sort, but we made the decision not to teach that until we've talked about heaps next week. So we added a little bit more to week 9 and a little less to week 8. So I don't think shell sort is what... I don't actually know what the Linux style sort is. I don't know. Um, so Waleed says, is it too early to ask when I'll talk about the exam? That's a good question. So my intention is to get information about the exam up here for next week, the start of next week, right? So I want to have something up here Monday that kind of just gives you an overview of what an exam for 2521's about. And then in week 10, we actually have some lecture time to talk about the exam. So that'll come in week 10. Week 10's just pretty much we talk about the exam, we do some revision until people run out of questions and things to talk about. So yeah, Diora says, will we get any practice or past exams to look at? Yes, I'm sure that there will be some past exams. I don't know is the short answer, because I've spent zero time thinking about the exam in this course, literally zero. So, but like unless we literally don't have anything, which I'm sure we'll have past exams. So nearly probably, unless something terrible happens. Yeah, and questions about exam scheduling. I have beyond zero control over exam scheduling, sadly. And even if there are issues with schedule, I don't deal with them. They're dealt with centrally through the school. So I too will pray for you and your personal circumstances surrounding exam timing. So, Quicksort. We talked about 3 basic n-squared sorts on Tuesday, and then we talked about merge sort on Tuesday, which was a cool sort, and as I told you, my favorite sort. And now we're going to talk about quicksort. Now, a way to think about quicksort is that think of it like the sibling of merge sort, right? You've got your 3 n-squared sorts that we talked about, your selection sort, insertion sort, and bubble sort. And then we've got our potentially n log n sorts, which are more complicated, more difficult to write, recursive, and they have a similar best case complexity, which are merge sort and quicksort, and they're both recursive divide and conquer algorithms. Now, the reason we're learning about quicksort is the exact same reason we're learning about merge sort. It's because for large data sets, we really need an algorithm that isn't n squared time in the best case, or potentially average case. And quicksort's just another way of doing that. Now, at a high level, before we get into the quicksort algorithm, if you were to try and weigh up merge sort and quicksort, the general difference between the two, right? Firstly, like they both are mostly implemented recursively, which, as we've learned in previous weeks, can be an issue at scale. You can do some of these things iteratively, but like think of it recursively. The standard trade-off is that merge sort, as we talked about yesterday, requires an extra data structure. It actually requires mallocing memory and this temporary piece of data as you sort. Now you might think, oh, okay, well that's not that bad. It was just an array, right? Well, the problem is, like, let's say you're sorting, 1,000,000 elements. It's like 1,000,000 elements times by 4 bytes, right, is, 4,000,000 bytes to megabytes. So like, if you're trying to do a sort of 4,000,000 items, you're immediately looking at mallocing 4 megabytes of memory. On some systems, that could be non-trivial, right? Like that, it can be a non-trivial amount of data, and obviously that can go up substantially. So that's kind of the one downside of merge sort, is that you need that extra memory. The downside of quicksort, because it doesn't need that extra memory like merge sort. Quicksort's like the other kinds of sorts we deal with that can just do things in place. The downside of quicksort, however, is that quicksort has a worst case time complexity of n squared. So, but there's ways we can mitigate that. I won't go into the details too much now, but it's like the reason it's n squared, you can actually make that better through the algorithm. It's not like a bubble sort or something, or a selection sort where it's just n squared all the time, no matter what. In the worst case, there are ways we can mitigate around it. But let's first talk about what in the world quicksort is. Quicksort, I remember this learning it the first time. It was the one sorting algorithm I think that kind of confused me the most at the time. In hindsight, I'm not too sure why. I think I just didn't come at it the right way, because it's not actually a very complicated way to sort. But the idea is, and before we get into all the diagrams and stuff, if I just get a list of unordered numbers, see what, again, I was not going to do this, but I changed my mind a lot. Unsorted numbers. Or I could just Google quicksort and see what I get. Quicksort. I'm sure they'll give me some kind of list of numbers. Yeah, great. So basically, I'll give you the really quick rundown of quicksort, which is pretty straightforward. I have a list of numbers like this. Sure, these ones have negatives. The way quicksort works is that you essentially you apply this recursively, but how you start off is you choose an item that you call a pivot, right? And what you do, sorry, actually, screw it. I'm just going to get you a GIF of this or something. I've changed my mind. I'm just going to butcher it. There's a bunch of YouTube videos around there on the internet that can kind of do this stuff for you. And I know showing you this at the moment, you might be thinking like, okay, this doesn't really make a lot of sense. But basically the way quicksort works is that you pick a pivot, which in this case is the number 3 to start off with. And then your job is to try and rearrange your list such that everything that is smaller than the 3 is on one side and everything that is bigger than the 3 is on another side. That's the general gist. So when you look at something like this where you have a 1 and a 2, the 1 and the 2 are now kind of on one chunk here, and all the other numbers are on the larger side there. And what this does essentially is it allows you, kind of similar to merge sort, to break your list up into a chunk of, that's more bubble sort, break your list up into a chunk of 2 separate numbers. So say you have something like this 3 here, right? So 3 is your pivot. So you start with a list like this, 3 is your pivot, and you say, all right, well, I need everything on the left-hand side here to be smaller than that pivot, and I need everything on the right-hand side to be greater than that pivot. So let's just say, you know, before we think too heavily about the algorithm, it's like, okay, well, you want to start swapping lots of things around so that everything to one side is like smaller than it and everything to one side is greater than it. You know, so your 9 over here is greater than 3, your 1 smaller than 3, your negative 3 is less than 3, your negative 6 is on the wrong side. So you're trying to move these things around so that you've basically got these two halves, and the halves themselves aren't sorted, they're just bucketed correctly. So what Quicksort's first job is, and we call this process partitioning, is it's trying to take a pivot, which we treat as like a middle element, and it's trying to get like everything smaller than it on one side and everything bigger than it on another side. And in a case like this, you can see that after doing some swaps, I've kind of created a scenario now where everything on this side is smaller than the 3 and everything on this side is bigger than the 3. Right? Like that. And now we know, well, if we wanted to, we could then say take this 3 and we can slap it in the middle, because we know that the 3 is between those values. Now you remember how with merge sort we talked a lot about dividing and conquering, in terms of like merge sort's objective is to try and break this problem up into a series of smaller problems, and we've actually kind of done the exact same thing here, because what we did was we took all of those numbers, the big list at the start, we found a pivot which we just picked as the last element. We could pick any pivot you want, but standard convention might be to pick the last element. Then we shifted it into two halves, and then we slapped that back in the middle. And then what you do is you basically apply quicksort. Oh, that was a really straight freehand line. My lord. Never again. That was gorgeous. And then what quicksort does is it does the exact same thing on two sublists. Like think about how merge sort worked, right? Merge sort broke it up, and then it just recursively applied the exact same logic to like progressively smaller and smaller chunks. And the exact same thing happens here. So, you know, quicksort will take this half over here, down like this, and it'll take this half over here. And it knows that, like, in a general sense, that all of these have to come before the 3, and then all of these come after the 3. So quicksort's like, all right, well, I got to do a quicksort on this thing. So what does it do? Well, it finds a pivot, which in this case will just be the 2, because we'll just grab the last element. So this is our new pivot, as in we want to resort this so that everything is left of that. Everything smaller is left of it, and everything greater is right of it. Now, in this case here, I'm just skipping the swaps part for now. In this case here, everything is already smaller than the 2. Okay, so that's kind of funny, because what happens is now the 2 is kind of locked in place. So the 2's all good. And we now just have to do a quicksort on the next one, right? So essentially, like, the recursion kind of keeps going. And then if we did the right-hand side, the pivot we're dealing with here, say, is a 9. And you can see in these two cases, it's kind of benign, because... get it? It's a pun. You know, because that's just how those numbers were ordered before. It's like, okay, well, everything's less than the 9, so I can't really put anything to the right of it. Matthew says, how do you just select the pivot? Well, there's some more complex ways to select a pivot, and there's some simple ways to select a pivot. The simple way to select a pivot is just to choose the last element, because in theory, a lot of these numbers are going to be ordered. It's just by a little bit of like happenstance that they appeared to be at the end in these cases. So like an example here is that if you look at this one here now, if I'm trying to quicksort this, I have a 5, a 6, and an 8. And if I pick this one as my pivot, because it's the last element, and that's just the rule we're following, what happens is, where do the 6 and the 8 go? Well, we know that they actually go to the right. So if this was, say, like if I just change these numbers around, let's say that, you know, one of these was a 4, for instance. Oh my god, that's a big 4. If one of these was a 4, then what we'd be wanting to do is like basically rearrange these so that, you know, everything left of here is smaller than 5, everything right of here is greater than 5, and then what we'd end up with is something like this, right, where 5's in the middle. And then similarly, you would do a quicksort on these two halves. So I'd be like, all right, well, I got 5 in the middle, and now it's time to do a quicksort on these two halves. But to do a quicksort on something like one element's trivial, because how do you sort one element? It's already sorted, right? Every list of one element is already sorted. And I know that probably got a little bit confusing as we got deeper into that, but the general point is, back to that first example, you're taking a list of numbers like that are all unsorted. You're choosing a pivot, which in the simple sense is just the last element. You're saying, okay, this is my pivot. Great. You're then trying to take this list and quickly and easily turn it into two smaller lists, where one list has everything less than 3, one list has everything greater than 3 or greater than the pivot, and then that will lead you to be able to apply that recursively downwards. So we're going to look at some more visualizations of that. There's some great YouTube videos on this on the internet. Like, a lot of this stuff is, you know, when someone spends tens of hours planning how to do a quicksort video and they put it up on YouTube, it's always going to be hard to not just say, well, that's a great way to go. But if we look at the algorithm now in a bit more detail, or I maybe shouldn't call it, well, this is a very high level algorithm. You take a list of numbers or items, whatever it is, you choose a pivot, which we're saying is just the last element. Then you rearrange or do what we call partitioning the array such that we have all the elements left of the pivot are smaller than it, all the elements right of the pivot are greater than it. This is exactly what we did in Paint, and then the pivot ends up in the middle. And then we recursively sort each of the two sides we partitioned in half. So it's just like a vaguely sort. You turn it into two halves, and then you just keep sorting those halves. This is easiest to implement recursively. It can be done iteratively with a stack if you'd like to. I haven't really spent much of my time in my life trying to do that because I think it's more confusing. The main reason we point that out is because, again, quite often iterative solutions don't run into recursive stack call overflows, because remember, when you're dealing with recursion, and we learned this with the Fibonacci stuff, is that your stack, you can kind of blow out stack frames and have, because remember, every time you do recursion, you're building like function calls on top of function calls, and eventually the computer can just run out of memory, or the program just essentially says, I don't have enough space to process all of this. So sometimes we like iterative solutions, even though they can be kind of more complicated. Strakar says, if there was an odd number of remaining numbers left of the pivot, how many spaces do we give for less than and more than? Well, you don't really like give spaces for less than or more than. Like, if this number here was 10, if this pivot that we picked at the end of the list was greater than everything, then we would simply sort the list into two halves, which would be this half here where everything's less than it, and then this half here where everything's greater than it, which just happens to be empty. This is assuming that 3 was 10. So there's no real, there's no real formal size or anything like that, and we're mainly swapping, as you're about to see. So what I gave you in Paint was a little bit more visual, but essentially, I think in this case they picked the first element as the pivot. But again, when I say the last element, the point is it's an arbitrary decision. Simple pivot choices essentially just pick a pivot. You could pick the middle element, you could pick the first, you could pick the last. If you're applying that same rule the same way every time, then that's like what you might call a simple pivot choice. And then there's more complicated ones we'll talk about. But if you look at something like this here, as you're, getting more conceptual now, this is your array of data. You've got all your numbers from your low index to your high index. And then what you say is that I'm going to quicksort this. And quicksorting consists of partitioning and then calling quicksort on the two partitioned halves. So I have my list. I say I'm going to grab a pivot. In this case, the pivot is the first element. Okay, so we're just grabbing the first element as the pivot. And then we say, let's rearrange everything else here such that we can put everything left of the pivot over here, everything smaller than the pivot to the left, and everything greater than the pivot to the right. These two halves, though, are unsorted. And I know I've said this like 3 times already, but I think this is one of the key things to understand about this, is that the partitioning process doesn't, like, it creates 2 sublists where those sublists themselves have a sense of less than or greater than, but that doesn't mean that they're sorted. And this is kind of the opposite of what merge sort does, right? Remember how with merge sort would create 2 lists like this. It would create like 2, 4, 8, and 9, and then it would create another list that's like 1, 3, 4, and 5. And the idea here is that these 2 lists themselves were sorted, but there was no sense that everything on the right-hand side is greater than everything on the left-hand side. Like, that's essentially how merge sort was trying to then merge numbers together. Whereas quicksort, the kind of concept we're dealing with here is that you might have two different lists, such as 2, 5, 4, 3, which is unsorted, but the right hand side might be like 7, 6, 9, 8, like that. So the actual two halves themselves aren't sorted, but there is a sense of order between the two halves where everything in one's less than the other. Srikar says, are we keeping the numbers in an array, or is there a better data structure to hold them? No, we're keeping them in an array in this particular example. And because we can do swaps on this, and I'll try and get some visuals up in a sec on it. But again, to take you through the process, it's like you find your pivot like X, and this is what happens. You leave your pivot there. You know how you're trying to sort things. You're trying to sort things into a less than side and a greater than side. And then what you do is you kind of have an I and J counter. Think of it like, remember how again with merge sort, when we merged those two lists, we just had like two little pointers that just moved along each list. We did that on Tuesday. So what we do here is a similar thing where we say, okay, well, I've got these numbers, and I'll just try and show you again with this example. You start out your two little pointers. You say, okay, well, I'm going to start pointing here. I'll call this one I, and then I'm going to start pointing here, and I'm going to call this one J. Okay, and then what you do is you move along those where you're trying to move I and J towards each other in the middle. So both of them are trying to move together and meet in the middle. And the idea is that anytime you come across elements where they should be swapped, you swap them. So as you say, let's say you're moving I from the left to the right here. You're going like here to here to here to here to here, like whatever. And all of these elements you're exploring are less than the pivot. You don't do anything, but the second you come across an element that's greater than the pivot, you wait until the J comes along and finds an element that's less than the pivot, and then you can swap them, and then you can keep moving towards the middle. So if we try and apply this algorithm more specifically to say, this example we had here, let me just get rid of all this crap, and then we can demonstrate it again. So we start off with our two like I and J here. And again, our job as part of partitioning is we found our pivot 3, and then we're trying to make sure that, like, I don't care where the line is. Like, I've had people ask me in the past, well, where's the left half and where's the right half? Like, where's the line? Is it everything here needs to be smaller? And the answer is, I don't know yet. I haven't gone through those numbers. So we still need to go through those numbers. So we start with I there and J there. And you know what? I's less than 3, 9's greater than 3. So I and J are probably in the right spot. So I move them along. I say, okay, I'm going to move I up here. I'll move J up here. -3 is less than I, so that's in the right spot. 5's greater than J, so that's in the... I already sorted these. Sorry, let me go back to... Is that better? That looks better. Sorry, I was like, I'm pretty sure these look pretty sorted. So scenario here, we have our I and our J. And 1 is less than 3, 9 is greater than 3. So those two things are in the right spot. So they kind of move along here. And I have -3 and -6. And it's like, okay, is -3 less than 3? Yes. So I think it's also in the right half. Well, I shouldn't call it half. It's in the right, it's on the correct side of the pivot. And then I look at the -6, and the -6, I go, oh no, I found -6 while I'm sweeping from the right, so it's probably in the wrong spot. I need to move it down to the other side. But the thing is, I don't want to swap it with this -3 because the -3 is in the right spot. So what I do is I keep moving my I along until I find a number I can swap. So here I'm like, oh cool, okay, I found a number I can swap. I've found 5 while looking from the left, which is greater than it, so that clearly needs to be on the other side. And I found 6 still on the right, which clearly needs to be on the other side. So I'm just going to take those and swap them. Okay, so, oopsie. So I take those, I swap them, and then because I swapped them, I can move my counters up again. Okay, and then what happens? I'm like, all right, well, 2 is less than 3, so it seems like it's on the right side because I found it with the I. I see that J is greater than 3 because it seems like it's on the right side. I found it with the, well, you know, whatever the J counter's pointing to. And then I keep moving them, and what happens is, like, think about how this works. I get here, now suddenly I'm like, ooh, I, or my left-hand looker, whatever you want to call it, found 6. And 6 is greater than 3, so this is probably in the wrong spot. So what did we do before? I waits here until it has something to swap. That's what we did before. But then the J moves along, and it points to the same spot, and now that it points to the same spot, that's kind of the signal for you that, like, you're done. You're like, oh, okay, well, if they've both met in the middle, then I've done all my swaps. So now what this tells you is because of how they met, you're like, well, okay, these are my two halves here. And now that you've found those two halves, where a condition is held here while they're unsorted, and a condition is held there while they're unsorted, you can put your 3 back in the middle, and now you get left with a list containing 2 unsorted halves. And that's what happens here, right? We start with our I, we start with our J, we move towards the middle until we find an instance where we have 2 elements that are on the wrong side. We swap them. You can see these 2 things here are swapped. Then we keep moving our I and J towards the center again until we reach the center. And once we've found the center, we say, I'm done. And then all we have to do now is pick up that X, drag it up and across, and dump it right between the 2. And now we have a list of this condition. And I think this last visual here is really important to dwell on because it kind of captures what the point of partitioning is. You know, because Quicksort does this partition process where it grabs a pivot and then it moves things into those 2 halves or 2 sections. And this is the condition that's held true. Your partition list should be made up of 3 sections. It should be a section where all the values are less than X, and that list is potentially unsorted. A middle section, which is just a single value X, and then a right-hand section, which is an unsorted list where all the values are greater than X. Any questions about this so far? I'm just reading the ones in the chat. So Matthew says, so this is good because comparisons are faster than swapping constantly. I don't like making statements about the speed of primitive operations because it's really hard to say that. I might come back to that in a bit. I'd say what's good about this is we can swap instead of having to move it to a new array, which again is just less memory having to be created. So we're applying a recursive divide and conquer capability that we wanted to with, say, our like we did with our merge sort. It's just that we're not having to create new memory to do that. Waleed says, will they meet in the middle if it's an odd number excluding our central thing? Yeah, they'll always meet in the middle. The I and the J will eventually overlap at some point, and that's how you know that you've kind of done the partitioning or finished the partitioning. These are just checks that you write in the code. Gorb says, what about duplicates? That's a great question. So I don't know if I wrote it in. I don't keep these things off the top of my head, but is Quicksort stable? Yeah, so I was going to say probably not. And it makes sense because if you think about how this algorithm works, like by default, this behavior that we've seen here, if you have a number 3 here, should you move it to the other side? Like, here's the thing. Let me maybe give you just a quick comment on stability when it comes to Quicksort. So let's say my pivot here is 3. And let's say that I didn't have a -3 here, I just had a 3. I butchered that 3. So you think, all right, well, is this stable? Well, it depends what my rules are. If my rules are that I move through this, and when I find a duplicate to my pivot, I just leave it there, you think, oh, well, that seems stable, right? Because this 3 over here started at the end of my list. So once I sort these 2 halves, let's just pretend this is sorted for a second. Once I sort these 2 halves, and then I put my pivot back in, it'll all be okay because, like my pivot's here. It's like, sure. That's still stable technically in that use case, but the problem is what happens if your 3 was in the right hand side? That's kind of a problem, right? So it's like if I had a 3 say in the right hand side here, where let's say this was a 3, and it's like I'm doing the pivoting and the partitioning. God Damn it. I'm doing the pivoting and the partitioning. It's like, do I swap that 3 to the other side? Because if I don't move that 3 down to the other half, then what's going to happen is when I eventually split up my array again, it's going to end up like this, whether the relative order of the 3 is swapped, right? Because that 3 that was our pivot started at the end of the list. That's where we chose our pivot from. So in that case, if you implemented the sort like this, then it's not going to be stable. I think one comment on stability that might go over people's heads is that stability is not a property that is always inherent to the design of an algorithm. It's not something that you can necessarily always infer from pseudocode. There are some sorts that are probably inherently stable no matter what you do. Well, actually, I don't even know, because most of it's implementation details. Most of it is how you actually structure it. Like if you implement a bubble sort one way or another, it could be not stable. If you implement an insertion sort one way or another, it could be not stable. There are ones that are kind of like, when we talk about stability, quite often we're saying that if you just implement this as it's designed without trying to be too smart or too thorough, then it's probably going to be stable or it's not. So the case of bubble sort and insertion sort, they are generally very stable algorithms. Because if you think about an insertion sort, if you're thinking about an insertion sort where you're taking numbers and you're dragging them down and putting them in the right spot, it's like if you have a duplicate here, if say this last element was 1, you're not going to put it in front of the 1 because that's just another comparison and another swap to do, right? So an insertion sort is stable just by virtue of how it's designed. You could still implement it and screw it up and make it unstable, right? Like there's nothing... You could make this a valid insertion sort that validly sorts things that is unstable because of your implementation. Quicksort's kind of the other way around. It's like, it's kind of not stable by default, but you... And this is not something, like I don't think we're going to go into this. It's something that you could make stable if you put time into it. But it's like if you just took the concepts we're talking about today and you took the code we give you, it's not going to be a stable sort. And yes, Srikar says, what advantage does Quicksort have over bubble insertion and selection sort? We'll talk about that soon, but it's basically just faster in most cases. And Alex says, when you insert the 3 into the middle, you have to shift all the greater numbers to the right. That seems quite costly. I really like Alex's question. So Alex kind of like, all right, well, let's assume for a sec that we sorted these. Let me just quickly resort these. So let's assume that you did the partitioning where you took the two halves and you you made them into two halves like this. And then it's like, all right, well, you've got your one half over here and your other half over here, but you've still got your pivot at the end like that. And it's like, surely it seems costly to kind of pick up that pivot and then shift all of these along. And we know that array shifting is an end time operation because you can't just shift them all at once. You have to kind of like tick, 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 move them down. So isn't that costly? And the answer is yes, but the way I've been showing you visually has just been kind of conceptual. But in reality, what actually happens is you take an element like this one and you actually just swap it. And you can do that with Quicksort because remember, your job is not to maintain any kind of order in the two halves. Your job is just to maintain two halves that themselves are ordered with respect to the pivot that are both unsorted. So swapping is totally fine. Like, yeah, sure, we've changed around the order of this little half, but it's like, we never cared about the order of that half. We know it's going to be unsorted. Our job is not to sort it right now. So when you actually slot that pivot into the right place, it's not a shifting process. It's actually just a swap process. And that's what makes that manageable. So that's a good question because that clearly would have been confusing based on the really high level way I was talking about it. So we've got some code here. We'll look at some visualizations at the end. We've got some code for Quicksort. When I said that Quicksort and merge sort are siblings, I kind of meant it in terms of they kind of look the same code wise. If you give them a glance, it's like merge sort was basically a post order recursive function where that we had our merge function which did most of the work. Quicksort is kind of like a pre-order divide and conquer style function where partition does most of the work. So with merge sort, we called merge sort on both halves immediately, which meant that merge sort's priority was to break it all up as quickly as possible and then bring it back together, which was where all the work happened. With quicksort, it's kind of the opposite, because we want to quicksort a list, but we actually want to do the partitioning and the swapping and stuff into two halves, and then we want to call it recursively. So it's actually another really good example of like when you're looking at like a dual recursion, like a tree style recursion, the kind of difference between like a pre-order and a post-order, where in this case we're doing the partitioning at the start. And just to really contextualize these three lines here, the partition and the two quicksorts, what that is it's like the process of, where's my first diagram? So we have a list here. The partitioning is where we take a pivot and we move all our items into two unsorted halves. That's the partition. So that's what that first step does. That's what that partition function called does. It tries to take your array, which looks like this, which is a whole bunch of unsorted crap, and turn it into something like this. And then you call quicksort on the left side and quicksort on the right side. And that's actually what's happening here in the code. We partition things to a left and a right, and then we call quicksort on the left and we call quicksort on the right. And then that exact same process just happens in smaller and smaller and more divided increments until everything's totally sorted. Now you can also see here that when we call partition on the whole list, partition actually takes in the array as well as the low end and the high end, right? Standard kind of sorting practice. But it returns a value. That was one thing that merge sort didn't do, right? If we think back to the merge sort, it was just like, it just did merge sort, and then merge, like that. But the reason we need that here is because partition's job is also to figure out what the pivot is. Okay, so partition is this abstraction that actually finds the pivot, swaps everything to be in two halves and stuff. So this I here refers to an array index that's the pivot. So it's like after the sort, I'm going to have my array is going to have all the standard indexes that it kind of did before, right? It'll have exactly 9 items. 10? I can't. 7? 8? 9? It'll have 9 items in it like this. And what partition does is after it finds that pivot and swaps things around so it looks like this, it actually returns you that 4. So that I here in the algorithm is that 4 that it returns, because when quicksort is applied to the left half and the right half, you need to know what that middle point is, because quicksort doesn't always perfectly sort things in half. Sometimes you'll get scenarios where like this is one half and then here's your pivot and then there's the other half, and that's kind of the more common case. So that's why I haven't liked my use of the word halves here, because it's not really a halve, it's a side. It's just the left side and the right side. Sometimes the left side is empty. Sometimes it's all of the elements. Sometimes it's half the elements. So to apply it recursively, we need to know where the middle is. So therefore we say, let's quicksort from the left-hand side to just before the pivot. And then let's also quicksort from just after the pivot to the right-hand side. So we're kind of like, let's quicksort from here to here, and then let's also quicksort from here to here. And then the quicksort algorithm's applied recursively. And just a reminder, when we say things are applied recursively, that just means that when the quicksort algorithm's called again, it's just trying to sort these numbers. It doesn't know about anything else. So you can just keep applying the same logic over and over again. Vincent says, so in the pseudocode, it's chosen the first element to be the pivot, and then it returns the new index of the pivot. Yeah, so that's a great question there as well, Vincent. So if you have a list of numbers like this, for instance, your partition function will choose a pivot. It might choose the first index or the last index or the middle index or whatever. But let's say it chooses the first index. Once it actually does the partitioning of this, which again, if we just want to step through how this works, so this is the pivot. So we're trying to partition these two things into halves. I'm going to get my left pointer. It's not really a pointer, like as in it's not like pointers to memory. It's just like a cursor. I get my left pointer, my right pointer. I say, yep, 5's less than 6. Perfect. And then I come over here and I say, is 4 less than 6? Is 4 greater than 6? No, 4's on the wrong side. So I'm going to keep this here until I'm ready to swap. So then I move this one along. I say, okay, is 3 less than 6? Yep, perfect. I move this one along again. Is 1 less than 6? Yep, perfect. Is 8 less than 6? No, that's in the wrong spot. So now I'm going to swap these two. Great, and then I move both my cursors along. We'll go through the code for this in a sec. I might be simplifying some things. And we say, all right, is 7 less than 6? No. All right, and is this one greater than 6? No. So they're in the wrong spot as well. So now I can swap those two things. Now I can't remember the exact way that we swap the pivot. I'm pretty sure that you have to swap it with an element that's like, in this case, you have to swap it with something that's in the left side, because you can't swap it with something over here because you're moving it from the left. So in this case, I take my 2 and I say, all right, we're going to swap that with the 6. Perfect. And now what we have is we have an array where we know that this is 1/2 less than 6, and this is another half greater than 6, and 6 is our pivot. But in terms of indexes, what the partition function will actually return here, right, because these are the indexes of the array, the pivot function is going to, sorry about that, 4, it's going to return us a 5, because the 5 is the index of where the pivot got moved to at the end, I think. And well, I'm sure. And that's what that partition function actually returns. So yeah, this makes sense. We partition it, we get the index of where the pivot got moved to, and then we quicksort the two halves. The real question then is, okay, well, what is this partition function and how does it work? Well, okay, it takes in a high and a low, and we know from previous experience that its job is to take in those two things and rearrange it about a pivot. Now, this particular partition function is using the first element of the subarray as a pivot. It's doing exactly what we did before. And then you can see what it's doing is it is using a for loop forever. So this is a for loop with no initialization, no condition, and no increment. Basically, it's the equivalent of a while true. I'm not really sure why this code example has that there, but a while true I think might be a bit clearer. And then you can see what we're doing is we set our two cursors. These are those two green lines I had, where we set the first green line to be 1 past the, if I unwind this again. We set our first green line to be 1 past the pivot, and our second green line to be the end. So low plus 1, then j equals high, so we got our two cursors, and then all we're really doing now is we're just, we have a little while loop where we're essentially just moving one cursor along until we find an element that's in the wrong spot. We stop there. We move the other cursor along until we find an element that's in the wrong spot. So that's the second while loop. So this first while loop is like move along to there. The second while loop is like move along to there. And once you find those two elements that are in the wrong spot, you swap them. And then you go back into the loop and you keep moving towards the center. This is quite a literal description of the process we described. And you can see we've also got this if I equals j part here, because as I said, if those two cursors end up overlapping, that tells you that there are no swaps to be done. So you just stop. There's no swapping to be done. You just leave. Then the last step here at the end of the partition algorithm is to say if a of I is less than the pivot. This is just some funky fence posting stuff to make sure that like you're actually swapping the right element. And then we actually swap it. So this last swap here is to swap it from low, which is the old pivot position, to the new pivot position, because if you remember, we took this out and we kind of ended up putting it, I think, here. So that's what that last swap actually is, and we're swapping it from the original pivot position to J, which is the new pivot position. And this line here is about making sure it's the right spot to swap it to. There's some funky logic you could, if you looked at that for a bit longer and you played through it yourself, you'd kind of figure out intuitively to you what that means. And that's pretty much like the implementation of Quicksort. It's actually quite simple. It's very easy to visualize as well, because while it is recursive, it's not like merge sort, which can be, I think, more challenging to understand the recursion. Now, when we get onto performance, the best case of Quicksort is O of n log n. And the reason that the best case is O n log n is similar to merge sort in the sense that partitioning is an O n time operation. Because remember, partitioning is not sorting. Just to like reflect on this a bit more, to fully sort an unsorted list is typically always n squared. Like that's just kind of how it works. The reason that these algorithms are faster is because they aren't necessarily doing a full sort on an unsorted list, right? A merge sort, most of its complexity is trying to merge two sorted sublists, and most of Quicksort's complexity is just trying to partition into two unsorted lists. And you know, partitioning into two unsorted lists is a lot easier than sorting everything. And merging two sorted lists is a lot easier than sorting everything. So both partitioning and I guess for that fact merging from merge sort, they're both ON operations. So partitioning is really quick because you just have two counters, they just go towards the middle and then they reach the middle and that's it. So there's n steps, right? Because you're only just starting at the ends going towards the middle. There's a total of n steps. With Quicksort, like merge sort, the real question is how many times do you have to do this operation? And the answer for that one is, in the best case, O log of n. Because it's a divide and conquer algorithm. So, you know, if you have 8 elements, like that, if you have, you know, all these 8 elements here, and you can partition into two halves, and then those two halves can get partitioned into like two smaller halves, right? Like, if you can kind of get this down, it's just like merge sort. How many steps do you have? Well, the answer is if I have 8 items, the number of steps I have is log base 2 8, which equals 3. So because it is recursive and it does divide things equally in the best case, the overall complexity is n log n, because there's the cost of on, which is the partitioning, and then there's the cost of o log n, which is just the number of times you have to partition it. Because every time you make another recursive call, you have to partition. So I guess I just want to point you back to the merge sort diagram I made you, which, well, I did this in Paint yesterday, but remember how I said like the cost of merging is on, and this is like one whole merge because there's 8 merges to happen there, there's 8 merges to happen here, and there's 8 merges to happen there. So we're doing the on 3 times, and it's 3 because it's log 8, which is, you know, log n. So it's the exact same thing with Quicksort, where every time we partition, it's on, but the question is how many times do you partition? And you partition exactly log n times in the best case, because you've perfectly split it in half. This leads to the question, though, what happens if it's not split in half perfectly? Why would it not be split in half perfectly? Well, I have a simple answer for you. It's because you chose a bad pivot, or because the pivot wasn't very helpful. In that case, it's n squared, and I'll explain to you why that's n squared. If we take a list of numbers, like 1, 2, 3, 4, 5, 6, 7, 8. And you look at those numbers and you think, all right, it's time to quicksort that. And we use the algorithm that we've just done. What do you do with that algorithm? Well, you choose your pivot, you partition. So we do this on operation. It's always on, partitioning is always on, it doesn't matter what the list is comprised of. So we pick our pivot and we go great. And then we get our 2 counters, our I and our j. And we say, is 2 less than... Let me do this another way. That'll save us some time. So in this case here, let's say we choose the last element as the pivot. That's probably what I meant to do. Did I? No. Let's just stick with what we're doing. I think I've confused myself. I don't want to waste your time as I unconfuse myself. So we've got our pivot, which is our 1, and then we say, let's try and sort all these. And like, what's going to happen here is that we're going to look at all of these and we're going to say, all right, is 2 on the wrong side? Yes, because we expect that our I counter finds things only to the left of it. So it says, all right, well, I want to swap this one. This should be on the right-hand side, right? Because I's trying to make sure everything it sees is on the left-hand side, and J's trying to make sure everything it sees is on the right-hand side, and they meet in the middle. So in this case here, the I sees the 2. It says, oh, no, this has got to be on the wrong side. I'm ready to swap this one. Okay, Jay, you go through the list, and you tell me when you find something ready to swap. So Jay goes through, and it says, all right, well, 8 looks good, 7 looks good, still greater than 1, 6 looks good, still greater than 1, 5 looks good, 4 looks good, 3 looks good. And then it gets down to 2 and it overlaps here. I should make this just a little bit more narrow. It gets down to 2 and then it's like, yeah, 2 looks good as well. And how does the algorithm work? Well, the algorithm works by saying once the 2 I and J's get on the same spot, you break and you stop doing the swaps. So what happens then is the algorithm works for us and we end up with 1 as our pivot where this is locked in place. And then we end up with the other half of our list over here, which we then have to call Quicksort on, and we have to call Quicksort on the whole thing. And what happens when we call Quicksort on that whole thing? Well, we pick the pivot again. We pick the first pivot. And then what will end up happening is that we'll loop through all of these, and remember every partition is ON, complexity. So then we'll end up locking in this pivot, and then we'll end up doing Quicksort on all of these. And what ends up happening is because the list is perfectly sorted already, and the pivot choice is always at the front, the same would apply if it was at the end. What ends up happening here is that we have to do our ON operation for the partition exactly n times, because we have to partition once for every element here. So this is how a quicksort can end up being n squared in the worst case. And the reason it's n squared, as we said, is that the worst case is when every choice of pivot you make is one of the highest or the lowest values. So if every pivot choice you make is the highest or lowest value, then it's going to be n squared in the worst case. If every choice you make of the pivot gives you the 2 equal size partitions, like if it always splits it in as much half as it can, 4 or 4 or 3 and 4 for odd ones, then you're going to end up with a perfect n log n algorithm. Now we will finish off this topic and we'll do a slightly delayed break, so bear with me. The last couple of things on Quicksort, well, we've just talked about the challenges of choosing a good pivot. There's one thing we can do to choose a better pivot, and that is using a medium of 3 pivot, where instead of picking the high or the low element, right, or a random one, because it doesn't really matter. Like, some of you might be thinking, oh, I'll just pick a middle element. I'll just pick the middle index. It's like a couple things. One is if you just pick the middle index and you look at an example like the one we have here, you probably think, oh, that'd be perfect. I'll just go the middle one and then I'll probably get like a 4 or something, and then that's a great pivot. Yeah, that makes sense for this example. But like, there's nothing statistically stopping you picking the highest or lowest number at any point if your choice is totally arbitrary and your list is very random. The other problem with picking a middle element is the way that the quicksort algorithm works is that because it has these like little pointery things that start here and move towards the middle, you actually kind of need to get rid of your pivot. So like if you were to pick the middle element, the middle index as your pivot, you would actually need to take that and then swap it with something at the end anyway while you do your partition. Because the partition kind of needs like, it can't have the pivot in the way. It needs to have these like 2 little counters moving towards the middle and meeting each other. So your pivot always needs to get swapped out to the end anyway. That's actually why we pick the first or the last element as the pivot for a simple pivot, because it's already out of the way, right? It might seem unintuitive, but if you pick a middle element, statistically you have no higher chance of picking a good pivot if the data is totally random, but you still actually have to do the swap operation to get it to the end. And that's just more time that you don't want to spend. So rather than choosing the middle element randomly, or like which has that cost I just mentioned, or we pick a high or a low element, one thing to do is to use a median of 3 pivot choice, which basically says I'm going to look at the I'm going to look at the first index, the last index, and the middle index. And they're going to be 3 random numbers. And then what I'm going to do is I'm going to rearrange them such that the lowest numbers on the left, well, sorry, I'm going to reorder them to ensure that like Z is always less than X, which is less than Y, and then that helps me choose my pivot at that point. So what we mean by that is that if we pick these three numbers, we want to rearrange them such that the smallest value at one of these indexes on the left, one of the smallest value, the highest value at these indexes on the right, and the middle one is in the middle. And what median of 3 basically allows us to do is look for a pivot, look for the best pivot, which the best pivot's going to be a number closest to a median, right? The median of the whole list, by looking at 3 different numbers. So we have a slightly higher chance of getting a good pivot, because if this one's a bad pivot, or if the high one's a bad pivot, then maybe the mid, like we have 3 chances of getting it right. So you choose 3, you hope that one of them's good, and then you rearrange them, so you swap them around. So the smallest number's here, the highest number's here, and the middle number's here. Now what the median of 3 does as well is that you can then, it's quite interesting to think about. If I take this, you can then be like, all right, well, if I know that Z is less than X and Y is greater than X, because like these are just random numbers. Like let's assume for a second that low was like 7 and Z was like 2 and high was like 4, right? So you'd rearrange them so that you'd swap them, literally just swap them, so that your 7, 4, and 2 is like that. The cool thing is, what you know is that you don't need to sort this Z anymore because it's already sorted. Because what is partitioning trying to do? It's trying to put everything to the left smaller than it and everything to the right greater than it. So that X, that Z and that Y are now in the right spot technically in terms of the partitioning. And then we just have to partition all of this stuff here. And you can see what I just mentioned before. To partition, you need to make sure that your pivot, which we chose as this middle value, is at either end, so you can, you know, do that little cursor thing towards the middle. So we do that. We put our pivot down at the start. We partition this, and then we get left with this at the end. So we partition this. The X ends up back in the middle like this. This is where it ended up. And now we have 2 halves. This one here on the left and this one here on the right. And you might be thinking like, oh, that sounds really costly, because I not only have to look up 3 indexes, I have to swap those 3 indexes. Once I've swapped them, I then have to also swap the pivot to the start or the end so it can get out of the way for the partition to happen. But all of those operations, in the grand scheme of things, are relatively cheap compared to having to approach like a n squared thing. Because again, if you think about it and you say, okay, well, what's n log n? Like, let's say you have a list of like 10,000 things. It's like an n squared operation here is 100 million? 100 million, I think. Yeah. An n squared is 100 million. But like an n log n is just going to be whatever the number is. It's going to be something like, you know, 25,000. So sure, it's like if you can help something approach n log n, even if there's some kind of little extra overheads, it's like there's no way that a few extra swaps are going to make this one much slower. Now that's quite an extreme example, but the point is that trying to get a good split has massive performance benefits. So yeah, again, the improvement's pretty much just the less partitioning you have to. Partitioning's costly because it's ON. The less you have to do, the better. And finding the right pivot, or at least using a cheap heuristic like this to find the right pivot, will save you that time. So it's a little bit of a cost now to save you a lot of cost later. Because you got to think about it too. It's like if you have 1 million items in a list, if you can find the right pivot and break that into like 2 halves of 500,000, that's going to be a massive cost saving compared to having to do like another whole thing. so it definitely has a bigger impact at scale. Yeah, Diorora says, why don't we prefer merge sort? Why don't we prefer merge sort to quicksort if it's always n log n? The two big things are, I would say probably the biggest thing would probably be space, because the two areas merge sort fails in, I think, at least from what I understand, is that one, merge sort needs that extra memory, so it's a lot of mallocing potentially. And then two, so it uses more memory. And then two, because merge sort I think is harder to create iteratively, it also means that if you have constraints with like what you can do on the stack, like the call stack, then merge sort could have a recursive stack call error potentially too. So I think it's a lot to do with space. At least that's my understanding. I might be missing something though, but yeah. So it's a lot to do with space. Diorora says, because it's recursive, does that mean that you would do median of 3 for each partition? Yes, that's correct. So every single time you do another partition. So once you then do a partition of these ones, like these two halves, these two sides, you then do another median of 3 to find the right pivot for each partition. Vincent says, after swapping the 3 values, i.e. this line here, do we always choose the new middle value to be the pivot? Yes, because like there's a good chance that if you pick 3 numbers, that the number that's in the middle of those in terms of ordering is the best pivot because it's in the middle. Like it has a higher chance in theory. That's not always true. Like imagine if you had a list of numbers from 1 to 10 or 1 to 100, and then you did the median of 3 thing, and the 3 numbers you got were like 80, 90, and 100. Sure, based on the median of 3 rules, the 90 would be the best choice, but it's like you don't actually see all the numbers here. So 80 is actually the best choice here. So it's a good general rule. It's probably going to help you win out in most cases, but it doesn't mean that like it's always going to be a better choice in every single particular iteration of this algorithm. And then it's like when you get into the real world, what ends up happening is that if you're trying to implement a really effective quicksort, you might then say, well, I have a quicker way to do this. Why don't we just store some other kind of data structure that tells me what the 1st and 10th and 20th and 30th, 40th, 50th, 60th, 70th, 80th, 90th value is. So I have like a rough indicator. And then every time I do a median of 3, I can just select maybe 5 elements and see which one falls closest. Like you could do things like that use up more memory, but again, and that would speed it up, right? But suddenly now you're creating a system that's both more complex and is using more space anyway, which is one of the things you wanted to avoid. So if you're already going to need to start allocating more space, then you might as well consider using a merge sort or something like that. And these things are very circumstantial. There is no real like clear-cut winner. The real benefit for quicksort, in my view, is that it's an in-place sort that uses no more memory that approaches n log n. That's really cool. There's not a ton of algorithms that can do n log n. Not a ton of sorting algorithms that can approach n log n without creating more memory. So big plus in that category. So last thing on quicksort. Oh, sorry. This is the code for median of 3, by the way. You can read through this in your own time. It's like quicksort. I don't want to get into this, but it's like basically the way the median of 3 works here is that this approach, actually the median of 3 function rearranges your array for you. And it rearranges your array for you, and then it just gives it to partition. So the idea is like this is your array, use median of 3 to swap these around, and then you just give it to the normal partition function that might, look at it a certain way. I mean, you can go through this code. It all makes sense. I know you look at this, you might think, oh, whatever, but scary. But it does make sense. Like a lot of code, we can't spend the whole course me just dictating code to you. The last comment before the end of this one, and we'll take a break, is one thing you can do with quicksort is that, as we've said recursive calls have high overhead, and generally speaking, quick sorting a really small list is not going to save you much time, right? Because think about like any kind of logarithmic algorithm gets like more, like if you think about it, like what's the cost? These are the costs of quick sorting, and this is the cost of, think of it like this is an insertion sort for 10,000 elements, and this is a quick sort for 10,000 elements. Massive difference. But what happens if I'm trying to sort 5 elements? Well, 9 squared of 5, or 5 squared of 5 is, 25. N log n for 5 is what, like 12 or something? I don't know. 5 times log 2, 5. 11.6. So it's like, it's only twice as slow at that point. And that's assuming best case. That's assuming that it perfectly splits it as well. And in reality, that might not be the case. So sometimes for speed and to avoid unnecessary recursive function calls, you could actually design a quick sort to say, you know what, if like we keep partitioning these things down into smaller chunks, and if we finally get to a partition that's really small, just do an insertion sort on it. It's just going to be, it might even be quicker. It'll take pressure off the recursive call stack, so we're not trying to hold all these recursive calls separately. These are examples of how you can combine some of these algorithms to just avoid complexity and potentially save either memory or time, because there is no such thing as the best algorithm. There's just the right algorithm, basically, for a particular circumstance. So let's take a 10-minute break. Please leave some feedback as always for Quicksort, and pause the video if you want to take a screenshot of it, because I'll just hit the break, and then we'll come back and we'll have a chat just about a couple things and part of assignment 2. Yeah, so cool. Thanks everyone.